All right, welcome to our second video of Unit 6. This one's on solution concentration. Yeah, let's get started. So, in any solution, any sample of the solution will have the same ratio of solute to solvent as any other sample in that solution. That's kind of the definition of a solution. It basically means that if you have a solution, then any swallow of that from any spot in that will taste the same. Or if you're coloring a solution and you make a solution with color, every part of it will have the same color. That's, again, the definition of a solution. If any of that is false, then it's not homogeneous, which means it's not a solution. Okay, so for example, if I have, a beaker of, red stuff, pretend that's all filled. Actually, no, let's not pretend it's filled. Let me get a box somehow here. Okay, so this is a solution. Really bad color. Yep, red laser and, whatever. So the right one is a solution. The left one is not. Now, of course, you're not going to have a solution like that, but the point is that you have the same color everywhere. You don't have the same color here. So the ratio of our solute to solvent, typically that'll be some kind of your solute over your solvent, is called the concentration of your solution. So that's the whole point of this unit, is we're finding ways to relate how much solute we have for how much solvent we have in the solution. So the concentration of a compound can also be expressed, more so referred to, by placing a compound's formula in brackets. So I'm about to show you an example, but brackets, keep in mind, tend to refer to concentration. Concentration is going to refer to molarity. Try and keep that in mind, because then basically that means the concentration brackets refer to molarity. So you'll get that later, and we'll use it more and more. That'll, especially later on this unit. But again, brackets represent concentration. Could be a bit to write that down if you'd like. Okay. For example, the concentration of calcium 2 plus could be expressed as calcium 2 plus in brackets. I tend to think of that as the concentration of calcium 2 plus or the molarity of calcium 2 plus. Basically, both are fine because molarity is the most common concentration we're going to be using. Okay. Before we actually get to concentration, you need to know it's only really measured for aqueous solutions and gases. So pure solids and pure liquids can't really be determined, as we don't have a solute and we don't have a solvent. You can't really have really concentrated water. You're not dissolving anything into water to make it water. You can't really, water down water to decrease the concentration. It's just water. And pure gold is just gold. It's not concentrated gold. However, you can have concentrated solutions like acid, for example, which is just really any types of the acids that we use. As you can hydrochloric acid, we'll go with that one. You actually make it by mixing hydrochloric acid, hydrogen chloride with water, and you can add more to make it a stronger acid. You can add less to make it a weaker. That's because it's an aqueous solution. As a reminder, aqueous means our solvent is water. So the concentration of gases, as I said, can be measured. It does relate to how dense they are, but just keep in the back of your mind that we normally will use pressure. That'll help if you go to AP Chem. As a reminder, your objective for these set of notes are that you can do molarity, mass percent, and parts per million. Those are in your notes. And also that you can talk about dilutions. Neither of those refer to concentration of gases or what can be measured. It just will help you later in equilibrium in this unit if you can remember those parts. Okay, so we have three main ways to express concentrations. That's actually a lie. We have four main ways, and I don't know if you noticed, this actually isn't ways. I will edit that, honestly, probably over summer. For now, I'm just going to leave it. Anyways, four main ways. Feel free to pause this, write down actually these formulas, and come back in just a second. Okay, welcome back. So molarity, again, is our most popular. Notice the symbol is capital M. Molality, not too common, but it has a lowercase m. Parts per million its symbol is ppm, and mass percent is percent. Molarity is moles of solute, and so is molality on top. Molarity has liters of solution on bottom. Molality has kilograms of solvent on bottom. Please do not just remember moles per liter. It is moles of solute and liters of solution. Most of your problems are going to be started by trying to find as much as you can about the solute, solvent, and solution, and then just work from there, whatever the concentration you need. Parts per million and mass percent are the same equation. The million, though, we multiply by a million. That's what 10 to the 6 is. Mass percent actually refers to 100, so we multiply all this by 100. But both of them are grams of solute per grams of solution. Before I go on, it is important to note that molarity, sometimes if we've got 4.0 molarity, we'll call that 4.0 molar. That's how we'll actually say it. Just like for molality, will be 4.0 molal. You might see that in some of your tests or your homework. And SOLN is the abbreviation for solution. So you're not going to be tested on those, but you're going to be seeing them, so might as well make sure you actually know what they mean before you go on. Okay. As usual, spend a few minutes, try this. Except what I recommend you do is you start by trying to figure out what you know about your solute, what you know about your solvent, and what you know about your solution. Try to tell me what compound it is, or at very least how many grams or liters or whatever you know of those, if you know them at all. All right, take a few minutes and come back. Okay, welcome back. So the problem says that helium gas is dissolved in water, and we're expressing that in parts per million. Okay, our solute, in this case, is helium gas, since we're A, dissolving it in water, that's one clue, or B, we have a lot less of helium than we do of water, both of which make it our solute, and that says that we have 3.0 times 10 to the negative fourth grams of helium. We're dissolving that in 200 grams of water, which means water is going to be our solvent. And our solution then is just going to be both of them added together. We might be using the grams of these later, so I'm going to calculate that right out now. So that'll be 200 plus 3.0 times 10 to the negative fourth, which is equal to 200.0003 grams. I may not use that, but I found that it's really useful to basically start by trying to find all three of these and then use what you need. So, parts per million is equal to grams of your solute over the grams of your solution times a million. Well, we already have our grams of our solute. We have the grams of our solution, so plug them in. So you get, I'm going to leave that as 0.0003 grams, a little bit easier to write. Again, that's that number. Over 200.0003 grams times a million, you will get 1.5 ppm. If you got this without adding the 0.003, that's fine. That will normally happen, to be honest, with parts per million. However, it's a really good habit to always try to find your solution, which is typically just adding your solute and solvent together. So in this case, you're fine, but in the future, make sure you add them together to get your solution. All right, here's another problem that, again, going to give you a few minutes. Start by trying to find what you know about your solute, solvent, and solution. Figure out what concentration you're looking for, and go from there. Might as well help you. Cadmium is the element you're looking for, and you may want to know that it has a molar mass of 112.41. So with that, spend a few minutes and come back. All right, welcome back. So our solute in this case, well, we'll figure that out in a second. We're just going to need to know our solute, our solvent, and our solution. I'm not sure why it keeps not writing the top part of the S. So we have an 87-gram sample, contains 2 grams of cadmium, and we're finding that in molality. Okay, if this 87-gram sample contains 2 grams, that's saying that 2 grams of this are cadmium. The rest of it isn't, or aren't, whatever. So that means that in this case, since cadmium is basically in that sample and very small, that our solute contains, or is, our 2 grams of cadmium. Our solvent then, or more so, let's skip down, that 87 grams then represents our solution. And that means that our solvent is going to be basically 87 minus 2 grams of whatever we've got, which is 85 grams. So again, 2 grams of these are cadmium. That means 85 grams are not. We're just going to call that our solvent. We're going to assume that's what it is, basically. So we're finding that in molality. Molality is moles of your solute over kilograms of our solution, our solvent. All right, that means we need to find moles of cadmium. So 2 grams of cadmium times 1 mole. Sorry, that was an alarm I had on my phone. Over 112.41 grams. That ends up equaling 0.018 moles. 87 grams is, I'm sorry, we're not using that. Our 85 grams will equal 0.085 kilograms. You can just move your decimal 3 spaces to the left or divide by 1,000. That means our molality is 0.018 over 0.085, which equals 0.21 mole. And that's your answer. Again, find what you know about solute, find what you know about solvent, find what you know about solution, then figure out what stuff you actually need and use the information you originally found to get that. Just like we took our grams and went to moles, we converted our grams of solvent to kilograms, and then we just plugged them in and divided. There you go. As our last example, spend a few minutes, come on back. Reminder, look for solute, solvent, solution, figure out what you need, and get there. Come back in a few minutes. Okay, so as always, solute, solvent, solution. So we're saying that vinegar, that stuff I kind of drink, contains 5 grams of acetic acid. By the way, that's why it tastes sour, in case you'd like to know. Acids tend to taste sour. You'll learn that next unit. So vinegar tastes very sour because one of its main ingredients is a weak acid called acetic acid. Anyways, so vinegar contains 5 grams per 100 ml solution. Again, you've got that word contains. That means this 5 grams is our solute, and this 100 milliliters is going to be our solution. It also says solution. Calculate our molarity. So our solute is 5 grams of acetic acid. Our solution is 100 milliliters. And to be honest, we really don't know a whole lot about our solvent. I'll tell you your solvent probably is water, but we really don't know much about that. We can't really go grams and milliliters, so we're hoping we don't really need it. Fortunately, molarity deals with moles of the solute, which we can get because we have grams and a formula, over liters of solution. It doesn't actually care about solvent. Unfortunately, they already gave us milliliters, so that kind of makes our life doable. So to get to moles of solute, convert these to moles. We got 1 mole. The molar mass of this is about 60 grams. Again, that's from adding 1 carbon, 3 hydrogen, 1 carbon. The molar masses, add those all together. And that gets you about 0.08 moles. 100 milliliters. If you move your decimal 3 spaces to the left, you get 0.1 liters. That means our molarity then is just 0.01 0.08 moles over 0.1 liters, which, wow, I'm so running out of room, gets you 0.8 molarity. Let me box this to help you kind of find that a bit easier. So again, solute solvent solution. We didn't really know anything about solvent, but fortunately we didn't need to. Find your moles, got those to liters, divided them, we're done. So those are concentrations. Highly recommend you watch this again. It typically is kind of confusing, but if you got it the first time, congratulations. All right, we got one last concept. We got to talk about dilution. So when a solution is diluted, more solvent, typically water, is added to the solution. This is like, you know, my wife and I drink a lot of chocolate milk, and I don't like the chocolate milk as chocolatey as she does, so I tend to pour some normal milk into the chocolate milk to dilute it a bit. That way it's a little bit less like drinking straight chocolate syrup, which I know some of you like, but I don't like it all that much. Or that vinegar drink I drink. You know, I don't like drinking just pure apple cider vinegar, so I pour a lot of water in there to kind of dilute it a bit. So, thing you got to know is that will increase the total amount of solvent, like when you add water, that's actually the most common thing you do, but keep the amount of solute the same. Now, my hope is you're thinking, well, that's kind of obvious. I just need to officially make sure you know that. When I add water to my vinegar, I'm not decreasing my amount of vinegar. I'm increasing my amount of water. So instead of, let's pretend we have 2 grams of solute per 10 grams of solution. If I add more solvent, let's say we had 5 grams of solvent plus 5 grams of solvent. Yeah, we're going to pretend that's at 5 grams. That gets us 2 grams of solute, because that didn't change. But now we have 15 grams of solution. So it decreases your solution, but it doesn't change your solute. It does decrease your concentration, but it doesn't change the amount of solute. All right, that's our video, though. Thank you for watching.